Hybridization for beryllium fluoride and boron fluoride. Anybody? Hybrid orbitals exist. Well, a chemist named Linus Pauling developed hybridized orbital theory by studying the structure of molecules such as methane. Now, why did he do this? Well, if you look at just the geometry of the px, remember there's the px in geometry, that would be the horizontal plane. Then you got the py, which would be, vertical. And then you have the pz, which comes out, right? So that would be 90 degrees. So you would expect there to be a 90-degree angle, right? Well, that doesn't happen. You get a 109 because the bonds spread out a little bit. It says the molecular orbital theory tells us that the CH bonds in methane are formed by the overlap of each hydrogen s orbital with the carbon's 2s orbital and the py, pz, px. But there's a problem with this assumption. We know, as Pauling did, that the structure of CH4 is tetrahedral and that the true bond angles are 109.5. Carbon's p orbitals are lined up so that they are perpendicular at 90-degree angles from each other. So how are these tetrahedral sp3, should be sp3, overlaps possible? So sp3 is the tetrahedral shape. So how is that possible? Anybody? It's kind of a dispersion that's happening. That is, things are pushing away from your 90 degrees. So you're spreading out. So a 90-degree angle is, I guess you would say, more confined than a 109-degree angle. Does everybody see that? This is a wider angle than 90 degrees. So, I mean, my sons share a bedroom, and they do like to spread out a little bit. They probably would prefer to have their own room, but that's tough, So minimized is the energy when this hybridization occurs. The molecule basically spreads out, and it creates stability. That's the most important part about the hybridization process, is that if it didn't occur, methane would be unstable. Why? Because it would be fairly rigid, and things that are rigid tend to break pretty easily. Resist. If you're unstable, methane would be even more unstable than it is right now. If you take a match to methane, it's pretty unstable as it is already.
Like if you let it off in a room and you just light the air on fire.
Right. We talk about that methane carbon hydrogen bond there. It's fairly, I guess you would say, weak, not strong. So a match to it. What's even more flammable? Propane. You get into your longer chains of carbon, like So be aware that being exposed to methane gas can blow your house up. You've heard about people that left the stove on and then lit a match and her whole neighborhood blew up. So stuff is dangerous. So once again, this is linear. You don't see anything above or below it, so it's behaving like the SP. This one has that 3 bonds, so it's behaving like the SP2. We had a diagram of that last week. You'll see that it's got that PXPY, that tri-bond there. There's a fluorine, one above it. So it's behaving most like that sp2. Number of regions of electron density is 5. So that would be DSP3, that trigonal pyramidal. And then 5 would be D2SP3 octahedral. So if we look over here real quick and you look at octahedral, the octahedral has 1, 2, 3, 4, 5, 6 things around it. So how many electrons would octahedral have around it? Raise your hand. Sophia, what's 6 times 2? So you'd have 12.
Your polyatomic ion has both double bound and single bound. Consider the polyatomic ion nitrate showed figure 8.14a. Three equivalent structures can be used to represent
Okay, let's read. How about Garrett? No? About I want you to draw figure 8.14 in your notes. Now, if we look at A, you'll see that the bond is moving around, right? So on the first one at the top there, it's on the NO to the left, and then it goes, go clockwise, it goes NO to the right, and it goes NO to the top. So see how that bond is moving around? Now, if you look at B, what does B show you?
All those structures.
Typically kind of shows you like this hybrid. It says the actual nitrate ion is like an average of the three resonance structures.
Sounds right.
What'd you say? I just want to, clarify.
Oh, I said it's like they're together.
Okay. Well, they'll describe it as being like a hybrid. So we want to show you that up here on the overhead. There are two ways of really looking at this. You've got the hybrid, and then you've got the ion. That's not a hybrid. So let's scroll up here and show you the hybrid first. So we have these Renaissance hybrids. Write this down, Jake. Write this down. Renaissance hybrids. So you can see here that when you see the dotted line, they're putting a solid line here. A structure with Renaissance forms does not alternate between the forms. Instead, it is a hybrid of the Renaissance forms. Correction, the resonance forms. So that the structure is called a resonance hybrid. For example, benzene, C6H6, has two resonance forms with alternating double and single bonds. In the resonance hybrid, the actual structure of all of its CC bonds are equivalent, midway between double and single. Okay, so when you're looking at one that's not a hybrid, like the one beneath this, right here, these resonance forms are associated with the ion, or the charge here. So right here, the electron is charged on the carbon. This resonance form has the negative charge on the carbon right here. And this resonance form has a negative charge on the oxygen. So if you're looking at a structure like acetone, the question is, where's the electron charge? This is important because it's going to determine the nature or the characteristic of the acetone, how it's behaving. Where the charge is, remember, electron has to do with behavior. So if you're having some type of medical problem, they're trying to diagnose your behavior, they're going to treat your electrons, right? They'll give you aspirin, affect your electrons behavior. Your aspirin is not going to affect your protons, nor is it going to affect your neutrons. It'll primarily affect your electrons. So this is a behavior where these electrons are. You can test for this, is basically what we're saying. This behaves a little differently than this does. People are like, why is it behaving differently? Why is this acetone behaving differently? It's because of these resonance structures. And you might want the acetone to do a certain thing. You might want it to be more effective. Like if you're building a car and you want your car to be better performing, you might need this particular resonance structure. Make sense? If you get technical, that's when you start to, have more people want to purchase your product. Because you're like, yeah, that's it looks more advanced and might function better. It's cheaper to get methane, or correction, it's cheaper to get hydrogen from methane than water just because the bonds are easier to break. We talked about how if you strike a match, methane's pretty explosive. That means the bonds are fairly weak because they break easily. If you're reactive, that means your bonds are fairly weak. weak that is. If you take fluorine gas or chlorine, you pour it on your clothes, it's so reactive because the bonds are weak. Make sense? If you have something like carbon monoxide, really a triple bond, that those bonds are very strong. So it's hard to react. That's why plants don't like it. So up here on the board, Linus Pauling, was he a German chemist? Jake? What was he? Swedish? No, he was American. Yeah. So he was an American chemist, which was pretty significant because chemistry, has its origins really in Europe more than it does in America. It started over there, chemistry. So, what's that? Okay. So, if you look up here, the reason why we're talking about Pauling concerns electronegativity. He was the one that developed, he was the development of an accurate electronegativity scale. It's hard to read that. Was one of Linus Pauling's one of his many major contributions to the study of chemistry. So let's go back and take a look at the electronegativity scale. We know where it comes from now. So the Pauling electronegativity scale there. And this right here is in 4 Paulings. So what does 4 Paulings tell you? How much a element desires an electron. So fluorine has the strongest desire for an electron. So when we start subtracting these values, we're going to determine bond strength. So the whole point here is to see, what's the bond strength happening between these two substances. How easy will they be able to break? If they break easily, you're most likely going to have a higher yield, make more money. So once again, the purpose of chemistry is to predict the future. If you can't predict the future, then there's a lot of chaos. You're not going to make any money. So keep that in mind. Whenever you're at a company making something, like you're at Ford, they're predicting how many cars are going to be made that day. And when they don't make those cars, then problems result. Like somebody gets fired because something broke and wasn't noticed.
Atomic number within a period and decreases with increasing atomic number within a group. The scale of
We see the electronegativity values come into play. If the difference when you subtract the two is 1.7 or greater, then it's mostly ionic. If it's between 0.4 and 1.7, polar covalent. Less than 0.4, mostly covalent. 0 nonpolar covalent. So you can see an example right here where we have the chlorine. So we go over to the table and we find chlorine is Cl, and it has 3.16 as the electronegativity value. Does everybody see chlorine? 3.16. Then we're going to subtract the hydrogen, which is 2.20. So we go over here and we find hydrogen, 2.20 right there. And it ends up being 0.96. So what does that tell us about the bond between the chlorine and the hydrogen? What kind of bond is it? Yeah, it's going to be polar covalent because it falls between 0.4 and 1.7. Very good, Hannah. Excellent. When people go to the movie theaters, do you want to go and sit right next to somebody? You kind of want to spread out a little bit. Yeah, I want at least somebody over here not sitting. Right. I don't want anybody sitting in front of me because then I might not be able to see. Right. So I need a little dispersion like you see here with methane. It's dispersion from the other hydrogen atom. So you have, under normal circumstances, the movie theater is full and this is very unstable. And this would be normal circumstances, it'd be 109.5. If this were the case, methane would be even more unstable than it is. It already is unstable. You light a match, it's going to explode, right? Methane, it's in your home, natural gas. There are cases where people left the natural gas on and somebody lit a match and the whole house blew up. So this is already unstable. So this makes it I guess you would say, more stable because it spreads out. And when we say more stable, basically what we're saying is that it's going to resist breaking apart. It's going to give it more flexibility because it's spread out a little bit. It's got more room to move around. So at the movie theater, Nate, at the movie theater, you like to have your space, right? Well, most people like to have their space because it gives them more room to move around, right? To kind of stretch out. And if somebody happens to spill something, like some popcorn, you know what happens. It probably won't get on you if you're a little dispersed, right? It's true.
Resonance is a condition that occurs when more than one value structure can be written for a molecule or ion. The two or more correct
Resonance hybrids, the electrons are going to move around. It says a structure with resonance forms does not alternate between the forms. Instead, it is a hybrid of the resonance forms. So the structure is called a hybrid, a resonance hybrid. So the benzene has two resonance forms with alternating double and single bonds. In the resonance hybrid, the actual structure of all the CC bonds are equivalent. So if you can see right here, this is what they're talking about. You see a double bond right here? In this situation, it's a single bond, right? And here it's a single bond, and here it's a double bond. So what's happening is that this is a hybrid that they're all equivalent. That is, it's moving very quickly. The bonds are happening very quickly, so there's no way to distinguish between this and this. Does everybody understand? They're basically equal. So there's nothing that you can do, no lab test that you can do that's going to distinguish between these two resonance hybrids. Any question on that? This is an anion, acetone anion, so you're going to see some resonance hybridization happening here. This would be your acetone, and then it gains an electron, forming an anion. So these are the two hybridization possibilities. These resonance, these wouldn't be hybrids, these would be resonance forms that are possible. So if the electron is found on this carbon, in the lab it's going to test very differently. It's going to have a different characteristic. How do we know that? Because if you got a headache, what you going to do, Jamal? You're going to take some aspirin. And aspirin is going to treat the behavior that you have. Remember, 99% of your behaviors in life are going to be treated with the electron. What can we do to affect your electrical system that's going to get your body back in balance? So this is electrical. This is going to behave differently than where the electron is here. So these two resonance structures are going to be tested and show differences. You might prefer one over the other. Let's say you're manufacturing what? What you going to manufacture one day, Hope? You're going to manufacture something. What are you going to manufacture? A business. You like chocolate bars. You can make candy bars? Bark. Right? So Hope is making bark, which would be chocolate with things in it. And she's going to find a certain method that's going to help make, let's say, an ester better. This isn't an ester, but this is the formation for an ester. The carbon, oxygen, would probably use acetone. Acetone could be used in nail polish. I don't know, Hope you might change your mind and go to a nail salon. And the acetone with the anion here, or the charge here, might work better. Might be a better performer. Now, a lot of you are like, Mr. Steinreich, what do you mean? Well, if you go to a salon, my wife, when she gets her hair done, there's shampoo that the salon uses. It's about $70 a bottle. She wanted me to buy her some, but I just couldn't hit the buy button on eBay. It was just too expensive, $70 a bottle. That's kind of a lot for me to spend on some shampoo. But, if you got money galore, like if you're, I don't know, name somebody who's rich.
Donald Trump.
Donald Trump, you could probably afford the $70 shampoo. But me, that's not in the budget. I have 4 kids. So this right here is the ester or the formula for the esters, right? This would be associated with Hope and her chocolate making, because that's important to have chocolates with different flavors. So up here, when the charge moves around, that's going to distinguish between these two resonance structures. Once again, hybrid orbitals was developed by chemist Linus Pauling. Was he a German or a Russian chemist? German? Russian? No, he's American. I know, it's a trick question. He was a very famous American chemist. He was really big on vitamin C. So if you like search vitamin C, he was very big on like you taking vitamin C. That was his big kick. So what he did, he noticed some behavior associated with substances, specifically with methane. He studied it quite a bit, and he noticed that if you were to do your geometry associated with the S&P model, you'd have a bond angle of 90 degrees. Now, if you ever go to, let's say, a performance like the opera, or let's say a musical, do you like to have people sitting next to you? Most people don't. Most people don't want people sitting next to them or in front of them because you can't put your arms out. You can't like stretch your arms out, right? So you get a little bit unstable. You know, if you're sitting in there and the performance is going and you have to go to the bathroom, you got to like jump over 15 people. So you're a little unstable, right? People don't like that. If you want to go get some chips or something, you get hungry. Like if you're at a basketball game, you're sitting there and you see somebody walk down the aisle with, what do you like to eat? Some of those like German roasted nuts. You ever seen those? Those are really good. Those are wonderful. Also, they might have some taco salad or something, and they've got that, and they're carrying it down the middle aisle, and you're like, that looks really good. I might have to go and do that. But if you're in the middle of the aisle, you got to get up and jump over everybody and, you know, cause problems, spill their drink or something. So up here, Pauling noticed that the angles spread out. And what does the spreading out do? Like if you ever seen those airplane, I guess you would say, commercials where they allow you to have a place where you can spread out and lay down. You ever seen, they had one on Super Bowl. You might see the Super Bowl commercial about the airplane. I think it was Turkish Airlines, where they had the little cubby, you could go in and sleep. So it makes you more stable. This spreading out makes you more comfortable, and if you're more comfortable, you're less likely to be as reactive. Now, is methane reactive? Yes, it is. If you strike a match, it's going to catch on fire. So it already is fairly reactive in this state, but if it was in this state, it would be a lot more reactive. Now, most of you might not know this, Diana. Where do we get hydrogen gas from? Might know? No, it's typically extracted from methane. You can get it from water, it just requires a lot more electricity. So it's typically, if you can see, you got CH4, right? So you can get the hydrogens off of it in an electrical process. There's a process to do that. In steam methane reforming, methane reacts with steam under 3 to 25 bar pressure in the presence of a catalyst to produce hydrogen, carbon monoxide, and a small amount of carbon dioxide. So that's how they extract there's a lot of hydrogen in the methane. There's obviously 4 to 1, right? And then hydrogen can go on and be used in, let's say, electrical processes. The nice thing about hydrogen is you can generate electricity without having a motor or a engine. Right, so keep in mind the SP2 has this clover leaf type structure. See the clover right here. Not a 4-leaf clover, but the 3-leaf clover. 4-leaf clover would be more similar to the SP3.
Shown in figure 8.14a, 3 equivalent structures can be used to represent.
Equivalent means, it says equivalent right here. It means if you were to set up a scientific experiment to distinguish between this and this, they would look the same. So So the conclusion would be you can't tell the difference between these two because they're equivalent. Equivalent means equal. So what they're saying is that they move around so quickly, they can be either one of those, you're not going to see any difference. So that's a hybrid resonance structure. To this acetone anion, this one, if you set up a test, this would prove to be different than this one. Because on this one, the electrons are on the carbon. Now, can you test for electrons? Yes, chemistry is a study of electrons. That's what we're doing in chemistry. We're studying what the electrons are doing. The whole periodic table looks like it does because of the electron. Now, if you have, let's say, a stomach ache and you take something for that, what is being addressed? Diane? The electrons. When you talk about, an acid problem in your stomach, that would be an electron problem. So acids are known to donate protons and receive electrons. They're proton donors and electron receivers. There's two definitions for it. We'll talk about more of that later. But the point is that carbon right here has the electrons at this point. Does everybody see that? She might want to have this resonance structure in the nail polish remover because it works better. As you become more technical at your place of employment, if you do things just an edge better, people are more likely to go there. Now, costs can come into play, right? If it's really expensive. Like my wife, she goes to hair salon and the shampoo is like $70 a bottle, and she wanted me to buy it, and I was like, couldn't afford that. So I'm just saying that technical, where the electrons place can make a difference in performance. This is talking about performance. So over here, the electron is associated with where the oxygen is, and that's going to drive where the bond is. So there's a single bond here. Single bond, there's a double bond there. So when the electrons are here, you have a single bond. When the electrons on the carbon, there's going to be a double bond. Which one's going to be preferred? Well, if you look at this situation where you have a comparison to an ester, and if you look at the actual functional group, the acetone is going to prefer I think the acetone is on this side here. Yeah, acetone. It's going to prefer the double bond. So this one is actually preferred. Does everybody see that? Double bond is preferred. And you can see that there's a double bond there on the electrons at the carbon. It looks like a triple bond. So just be aware that there are some preferences. This might be a better performer because the electron's out here. The electron on the outside makes the anion more aggressive. Much more of a, I guess you would say it, a radical. Much more likely to bond with things. Chlorine is very much a radical. You put it in water, it's going to bleach your clothes, change your clothes because it's aggressive, it wants to become stable. Okay. Linus Pauling was an American chemist, and we studied just a few minutes ago that he worked with the, what? What did he study? He studied the hybridization. He was the one who understood that atoms like to disperse or kind of spread out a little bit to be a little more stable. Talked about methane. So he also worked on electronegativity. And why is electronegativity important? It measures the desire that an element has for an electron. So much of the periodic table is about doing what? Predicting the future. If you can predict the future, you can make things, and make things like for money. If you go into history class, what do they tell you in history, TT? What do they tell you if you don't know your history?
That the future will come back. And,
You're doomed to
past will
repeat itself.
Yeah.
If you don't know your history, you're doomed to repeat it, right? That's why you want to study history, but just studying history alone doesn't give us as much predictability as the periodic table does. we can predict things with about 80 to 90% accuracy because there are a lot of variables that come into play. I was watching a guy on YouTube make gold the other day, and just extracting some of the gold from the acid is difficult because it wants to hold on to it. So there are some procedural methods that can obviously be improved on to increase your actual. There's a theoretical and an actual. But chemistry allows us to predict when we react things. If you go into a chemical storage room, chemicals have to be placed certain places because they're known to be reactive and cause a fire if you don't store them properly. Like if you saw the movie last night, This Is Us, fires happen all the time because of things that can be prevented. Chemicals were stored improperly. Electrical wires weren't wired correctly because they used, let's say, aluminum in the 70s. And aluminum is not a very good conductor. Not as good as copper, because copper is a little more massive. Talked about that earlier, how they use copper because it's more massive and the electrons, it's harder to push it around, so it doesn't heat up. Whereas aluminum heats up a lot faster and you have to use a thicker wire. If you ever cut the two in half, you'll see that for the same voltage, if you were, let's say, running a 120, the aluminum wire would have to be maybe 2 or 3 times as thick compared to the copper wire, because copper wire is more massive. All right, so keep in mind that the scale up here is associated with reactivity. Fluorine is the most aggressive. It desires to react and produce new substances. So let's read a little bit more in the book to where we see the table on page 266, 8.7. What does percent ionic character mean right here on page 266? If you're an ionic bond, what does that mean? Talked about naming. The first thing you want to look at, it has a... Does water have a metal in it? Hydrogen is considered to be a non-metal. Does carbon dioxide have a metal in it? No. So if you have a metal in you, you're going to fall into that ionic characteristic. Now up here on page 267, if you look at the difference, you're going to measure the larger substance on top, that would be the numerator, minus the electronegativity. And then we have a difference there of 0.96. And if you go to your table, what does 0.96 refer to? What bond character is 0.96? Raise your hand. Harrison? Austin? What bond character is 0.96? It's between 0.4 and 1.7, which is between 0.4 and 1.7, which is Sierra? Polar covalent. Very good. Kind of a bellwork review is developed by a gentleman by the name of Linus Pauling. Now the question is, was he a Russian chemist, a German chemist, or an English chemist? Raise your hand. Linus Pauling.
You said German or?
Russian, German, or English? English?
I say,
English? English? Russian? German?
No.
He wasn't any of them. Yeah, he was shh. Sadie, he wasn't any of them. He was an American. I'm just checking to see if you know your American history or not. What? Think about it. If you said he was an American, I'd have given you points. Too bad. Shh, no. All right, quiet down. Shh. Quiet down. Now, Linus Pauling, shh, he was known for his studies on what vitamin? Raise your hand.
Chemistry?
No. C. He was known for his study on vitamin C. Is he from Russia? Is he from France? Or is he from England?
What's his name?
Linus Pauling.
I know what it is. Let's shine. Let's go.
Where's he from?
Poland.
He's from America. Very good. That's like 5 points. Yeah. He's a very famous American. And one of the things he was famous for, Alex, because I've done this enough. Yeah, his name's Linus too. Like Snoopy. He was very famous for his study in vitamins, specifically vitamin C. He really liked to take vitamin C, encouraged people to take a lot of vitamin C to stay healthy. He was a big vitamin C encourager. Now up on the board here, one of the things he discovered, he developed hybridized orbital theory by studying the structure of molecules such as methane. You see right here, 1 negative, NO3 1 negative. This is not a resonance hybrid right here. How do we know this is not a resonance hybrid? Raise your hand if you don't know what a resonance hybrid is. Okay, a resonance hybrid, if you look right here, you see there's a double bond? There's a single bond right here. With a resonance hybrid, these both are equivalent. What does that mean, Sean? These both are equivalent. It means you can't do a test to determine they're different. Everybody understand? So if you tried to test these two, you couldn't see a difference because the resonance structure is happening so quickly. And the biggest reason why you couldn't tell a difference is it's not charged. Usually when you do a test, you're looking for a charge. If it's neutral, you're going to have a hard time determining there's a difference. Everybody understand? Now back in the book here, when you're looking at NO3, this has a charge to it. So wherever the bond is, that's most likely where a greater concentration of electrons are going to be. And you can then test that. Right? Now the problem with NO3, Ethan, is that it looks so similar. See, it's NO3. So it really borders being a resonance hybrid because it's so similar. That's why I wanted you to draw it, because it would be very difficult to distinguish it. You could, where the electrons are, you could determine whether it's on top or the bottom. But if you flip it, it's going to be the same thing compared to the one I'm getting ready to show you. So if you put this in water, obviously this forms a positive cation. This forms the anion there. What happens with the sugar? Carbon comes off? No, one thing comes off. Noah, what comes off sugar when you put it in water? What? There's one thing that comes off.
Negative ions.
No.
Negative.
No, a hydrogen. So it ends up being C6H11O6, and I believe this is negative, yeah. And then because the hydrogen's positive, so only one thing comes off. So sugar's not very soluble in water. That means it doesn't break down very easily. This is still a fairly large thing. That's why it tastes sweet, because this is fairly large. Your brain wants this, the sugar ion. So if you're studying this, like this electronegativity, you're always looking at ways to make things that are going to dissolve and be similar to this. Like the amino acid, what's the amino acid that mimics sugar? You might know? In the brain. Phenylalanine? It's called phenylalanine. It's not really good for you because it stimulates your brain cells where it almost kills them. But we're trying to study things that will allow you to be less hungry at what time at night? After 8 o'clock. What happens after 8 o'clock? Right. Once you eat a lot after 8 o'clock and then you go to sleep, you basically form what?
Fat.
Right. Now, can you take chicken fat and make human fat?
No.
What happens? Can you store human fat as chicken fat? Or can you store that chicken fat in your body as human fat? No. You have to break it down. So most fats are discarded. When people eat before they go to bed, they typically don't eat fatty things. They typically eat what? Sugary things. They end up. What's something people might eat before they go to bed? Cereal. Yeah. High on the list. What else? Cupcake. What else?
Pop-Tarts.
Pop-Tart. Ice cream. I got a taste for some Graters. Graters ice cream. You ever had it? So good. Yeah. You ever had that chocolate raspberry? It's very good. What's your favorite flavor, Zane? Graders? Oh, the raspberry is wonderful.